Previously, we talked about solving right triangles, and in those problems, we were given 3 parts of the triangle and then asked to find the remaining 3 parts. And of course, one of the angles in those problems was always a right angle. So now we're going to look at similar problems, but in these problems, the triangles are oblique. In other words, they don't have a right angle in them. So in this section, we'll look at the law of sines, and then the next section, the law of cosines. And those 2 laws can be used to help us solve these triangles under certain circumstances. So in these problems, basically 6 cases can arise, and so we're going to look at that first. The first case is that we have all 3 sides given and no angles are given, and so we'll refer to that as the SSS case. So the letters here, either S or A, stand for side or angle, giving us the information of what part we're given. So SSS means all 3 sides are given, no angles are given. And to solve this one, we need to use the law of cosines, which of course we're not doing today, but I'm just going to put that there for next section. So law of cosines is needed to solve this case. We won't do those ones in this section. SAS means 2 sides are given and the included angle is given. So we know maybe these 2 sides, and then if this is alpha, you know, so well, let's use our usual way. So I'm sorry, I should go back and talk about how we're going to label the triangle. It's the same as we did before. So if we have our 3 vertices, A, B, and C, then the side opposite has length A. Side opposite is vertex A is length A, opposite vertex B is length B. These would be lowercase, of course, and then this would be length C. And then the angles we can refer to as the capital letters, but a lot of times in lecture I'll use alpha, beta, and gamma, so that we don't get confused between lowercase ABC, which are the side lengths, and then uppercase ABC are the angles, right? So if I use Greek letters, we don't get confused because there's different words. So this is what I have in the notes. Okay, I should have done that first, excuse me. Okay, so if I call this alpha, alpha is given, then alpha would be the side, or excuse me, A would be across from it. That's not actually given. So these would be B and C. So alpha, B, and C are given. And then beta, gamma, and A are unknown. Of course, we can relabel those in different ways. So in the SAS case, we also need to use the law of cosines. To use the law of sines, we need to know at least 1 pair of an angle and the side opposite of it. And once we look at the law, you'll see why. Okay, the SSA case. So notice in number 2 and number 3, we're given the same amount of information as 2 sides and an angle, but because of the order is different here, we can actually use the law of sines for this one. Here we know 2 sides, so say this is B and C, and then the angle given is not in between the 2 sides. So it could be beta or it could be gamma, it doesn't really matter. The key thing is we know a side and its opposite angle. So then if that happens, then we can use law of sines. So these are different cases. We can use different laws. And we prefer law of sines over law of cosines. It's an easier formula. So it's good to realize that the difference between SSA and SAS, where we can't use law of sines. And then I combined so I said there's 6 cases. This is 2 cases in number 4. So we could have angle, angle, side, or angle, side, angle. So like here I'm talking, we know maybe these two angles and then this side, right? I'll just call it A. Versus I know these two angles and this side. It doesn't really matter which angles we know, because once we know two, we can solve for the third by just subtracting. So we can subtract from 180 degrees to find the third angle. That would always be our first step, no matter which case this is. And so it really boils down to the same problem. So these two cases are solved the same way. Okay, so for this one we use law of sines. So for today we have this one and this one that we're going to use law of sines for. And then the sixth case, which I have as number 5, but since these are 2, this is really the sixth case, is angle, angle, angle. 3 angles are given, no sides. And of course in this case we could find infinitely many similar triangles, so the sides aren't really determined. And of course then we won't work with this because too many triangles are formed. We would need more information. So to find the lengths of the sides, since infinitely many similar, whoops, that's not how you spell infinite, infinitely many similar triangles would be formed. So we can throw this case out. We're not going to do anything with this. So we really only have, the 5 cases, but really 4 because these 2 are the same. So these are the ones you want to focus on. Make sure you can understand the difference between these cases. All right, so like I said, we're going to work with these 2. Well, actually 3, right? But these 2 that are really the same case are easy to solve. This one is a little trickier, so we're going to spend most of our time on number 3. All right, first, whoops, I don't have anything on the back page. First, we're going to derive the law of sines. So, like I said, this works for oblique triangles. We don't have to have a right triangle. So let's put alpha in standard position. This is alpha. And we're going to create this triangle. So this is, if this is alpha, this is a side of length A. And then I'm going to label this as beta, and this is gamma. Right, so this triangle doesn't have a right angle. And then we're going to focus on the sine of beta. And if we want to find, just think about this right triangle right here. Then let's call this, excuse me, let me think for a second. Actually, we're going to form 2 triangles. What I need to do here, I remember what I need to do. So if this is alpha, this is of course a straight angle, so this is 180 degrees minus alpha. And so I'm going to actually form 2 right triangles. And note that the sine of alpha is actually equal to the sine of 180 degrees minus alpha. So, I put this in the xy plane here, right? Alpha. So this is the reference angle of alpha. And of course the reference angle is an acute angle. These have the same sign because the sign in, let me go back. Like I said, this angle is acute, so the sign will be positive. This angle is obtuse, but the sign is also positive because it's in standard position and lies in quadrant 2. Okay, so now we're going to find the sign of beta and the sign of alpha, but using the fact that it equals the sign of the reference angle alpha minus r. So now the sign of beta equals, so we don't know what this length is here. It's the height of the triangle, but maybe you want to call it the y-coordinate, right? This point here, that would be the y-coordinate. Whatever you want to call it, it doesn't actually really matter. And then we would take, sine of beta, it would be h over a or y over a, whatever you want to call it. And then the sign of alpha, which I'm using this triangle because they have the same sign, would be h over, so now I'm using this side, here's where it gets a little, excuse me, I called it h, but I'm using y, aren't I? So these are the same. They have the same height, these two triangles, right? So we have these two right triangles. We have to find the length of this side, but it is the side opposite of beta, so it's b. So what I want you to notice is that these both have y in it, or h, whatever you want to call it. So y equals a sine beta, and y also equals b sine alpha. Well, since these are both equal to y, that would imply that a sine beta equals b sine alpha. And if I divide both sides by ab, I get one of the formulas. This implies that sine beta over b equals sine alpha over a. Like I said, this is one of the formulas. There's actually another statement that we can conclude here, and that is that this is also equal to the sine of gamma over c. And I'm just going to put this down here. This is the law of sines. These can all be flipped, so these are ratios. They're saying the sine of beta divided by the length of its opposite side equals the sine of alpha divided by the length of its opposite side equals the sine of gamma divided by the length of its opposite side. So this third one that I just threw in here, we could just relabel the triangles and get that. It's easy to derive that. Once you have the first two, we can conclude the third as well. So we're going to omit that. So again, this can be flipped, and I'm going to use, like I said, I'll use alpha, beta, gamma, but this could be B, A, C, all capitals letters, of course, or uppercase letters. All right, so like I mentioned on the first page, to use the law of sines, we need to know at least one side and its opposite angle, right, or angle and its opposite side. You need to know one of these ratios, in other words. That's what this first bullet is saying. You have to know one of these ratios completely. In other words, you have to have an angle and a side opposite it. So when do we know that? Well, we know it for SSA case and ASA, or AAS, so when you know two angles. We talked about that already. This does not work for SSS because we don't know an angle, and SAS because the angle we're given, we don't have the side opposite. So these, again, we already said this, but we need law of cosines for these two cases. We'll talk about that in the next section. All right, so we're gonna start with, like I said, when we know two angles, that's the easy case. There's really nothing tricky about it because we can we have the two angles. We can easily find the third just using subtraction. So we'll do one of those first. And then we're going to talk about the SSA case, which is harder because, like I have in parentheses here, it's called the ambiguous case. It's hard to know how many triangles we're going to get in our solution just by looking at the information. You have to look at it carefully to figure out how many solutions you're going to get. So we'll spend more time on that. All right, back to the first problem here. So if we have alpha and beta, we can easily find gamma. And these are calculator problems. You have to have a calculator. I mean, you don't have to, but I'm not going to always give you nice, friendly numbers. So you should definitely always have a calculator when you're doing these. And make sure you're in degree mode because these angles will be in degrees, usually. All right, so gamma, don't confuse gamma with alpha, right? Gamma is upright, alpha is sideways. Gamma is 180 degrees minus 45.1 degrees minus 75.8 degrees. So even though that wouldn't be too hard to subtract the long way, I'm going to use a calculator. All right, so 59.1 degrees. So we found the first part. And then you can draw a picture if you need to. C is the side that's given. That's going to be its opposite of gamma. So, but you know, you really don't need a triangle, or I mean to draw a picture, because you should understand gamma and C are across from it, and that's one of the ratios. The formula is very easy to remember because of that. So the sine of gamma is 59.1 degrees over its opposite side is 10.2. That's our first ratio. And then it doesn't matter which one we solve for next. If I do sine of 75.8 degrees, then I want to have a B underneath it because that's beta. Or I could do sine of 45.1 degrees over A. Just make sure you use the right combination here, right? Don't mix up and put A here, then you'll get the wrong answer. At least labeled wrong. Okay, so what I usually do is I cross multiply and then divide. And I won't always write this step out, but usually I just do this all in one step, but I'll show the steps the first time. So B sine of 59.1 degrees equals 10.2 sine of 75.8 degrees, and then divide by sine of 59.1 degrees. Make sure you're putting degrees here, because if you don't, then you're using radians, and that's incorrect. So if for some reason you didn't have a calculator and you wrote that as the answer, I would actually accept that. That's shows that you know what you're doing, right? But we'll put it in the calculator to get a number, you know, helps with the number sense. See how big this is. So 10.2 sine of 75.8 divided by sine of 59.1. So I have my graphing one, but even if this were scientific, make sure you're closing off this parenthesis, otherwise you're not going to get the right answer. So parentheses around this, it knows to multiply. All right, equals. So that's approximately 11.5. And for rounding rules, what we'll do is if this is to 1 decimal place, then we'll round our answer to 1 decimal place. If that's 2 decimal places, then I'll use 2 decimal places. And notice that this is approximate, so you should use an approximately equal symbol. Okay, so we have B, we have gamma, we still need to find A. So we just use this ratio again, and then sine of 45.1 degrees over A. So this time I won't show all this work, but it'll be A sine, or A equals, excuse me, 10.2 sine of 45.1 degrees over sine of 59.1 degrees. So notice the angle is what changes, right? in our work, and then just throw that in the calculator. The only thing that changes is this becomes 45.1. And we get A, whoops, I should have put A over there. Oh, excuse me, A is approximately 8.4 if we round to one place. And B, I should have mentioned with the units, a lot of times in these problems no units are given, so we don't put any units down for our lengths. You could just put units, but you don't have to. If there were units here, of course, you know, if this said centimeters, then I'd label these with centimeters. And my angle, of course, should have degrees on it if these have degrees. And these problems will all be working with degrees, so make sure you're labeling. All right, so now let's talk about the SSA case. So this case gets tricky because it's hard to tell how many triangles we're going to get. So I'm going to talk about the different scenarios. So in the SSA case, I strongly recommend that you always, no matter what angle is given, whether it's alpha, beta, or gamma, you always draw it like a horizontal base, and then your angle will be in the lower left corner. I'm going to use alpha, but of course it could be a different angle. But that, you know, that's the only one given, so that one should go there. And then you'll be given the side opposite it, and you're given another side, so you're given two sides. The side you're not given is the base, if you draw it this way. So A is the one that's given, that's over here. So when you draw it this way, alpha is fixed, it's a certain size, right? Or the angle, whatever it is, it's given is fixed. A, or whatever side opposite, is fixed, and this is fixed. So it depends on how long this guy is. I'm said to use B. So if B is alpha is fixed, B is this long. The question is this length of A long enough to reach the base of this triangle? So this is H. If A is smaller than the actual height, then you don't, whoops, I messed this up because I was supposed to draw the picture here. Well, we'll just do this. This will be the picture. This will be the number of triangles. Okay, so no triangle is determined if this happens. The A that's given is not long enough to reach the base of the triangle. That's why I recommend you draw it this way. It might help you see under certain circumstances how many triangles you get. And if you're not sure, the math will give you the answer as well, and we'll talk about that. Okay, so then what can happen is that the A that's given is actually equal to the height. So again, we draw alpha here. B is fixed, and then A is equal to the height. Right? We don't know the length of this side. So it's got to, if A is equal to the height, it's got to be this long. In this case, there's just one triangle determined. All right, now here's another case. Alpha is still acute. This time, A is shorter than B, but longer than H. So here's H. So it's longer than this guy, but shorter than him. So what can happen is you can get, let's see if I can, oh, here's a green pen. This triangle is possible. Remember, you don't know the length of this side. And then this triangle is possible. These are both the same length, A, that's what's given. And so we have two triangles and two complete solutions if this happens. So this is the one, the tricky one we want to watch for. And when we do the math, you'll see what happens. All right, and then the other thing that could happen is that A is actually, so here we know alpha, and we know B, and A is actually longer than B. If A is longer than B, then there's no way to get these two triangles because, you know, if you try to put it in this way, it's going to go outside of the triangle. and then you wouldn't have alpha. So in this case, there's only, oops, let me make sure I'm on screen, barely, only one triangle determined. All right, so here's the, 4 situations if alpha is acute. If it's obtuse, so I'm going to draw alpha like this, and then we know this side, then it's easier actually. We're never going to get 2 possibilities, because in the 2 cases, what happens, this is your beta. You get beta is acute in the bigger triangle and beta is obtuse. Well, if you already have an obtuse angle, you can't have 2 obtuse angles. So there can only be at most 1 triangle. And what needs to happen is that this side opposite of alpha needs to be longer than B in order to reach the base of the triangle. Whoops, that's A. If it is not longer than B, then it doesn't reach the base and there's no triangle. So if we have an obtuse angle given, then there's only 2 possibilities. It's when that angle is acute where it gets a little hard to tell, right? That's when it's ambiguous. Okay, so let's go ahead and do some examples. And we'll see that the mathematics will support the picture. So I strongly recommend you draw a picture on these. It will help. So this I gave alpha. I'm going to, again, this one I gave beta. It doesn't matter what I call it. Draw it in the lower left hand corner, especially if it's acute, right? These are both acute. And make sure your base is, just draw it horizontal. That'll make it easier. Just, if you always do it the same way, it's easier. Okay, so here's alpha is 34 degrees. Then, see, we know the side opposite of it, and B is 2.3. And look at how short A is. So you still need to do the math to prove it, but you should have a sense that this might be too short to reach the base. That's always your question when you're doing this ambiguous case. Does this thing reach the base or not? So use your law of sines. Sine of 34 degrees over 0.75 should equal, so with the other side we know is B, so this should be beta over here. And the question is there going to be 1 beta or 2 possible betas? So sine of beta over 2.3. So 2.3 sine of 34 degrees equals 0.75 sine beta. So sine beta is 2.3 sine of 34 degrees, and then divide by 0.75. So put that in the calculator again, make sure that's in degrees. 2.3 sine of 34 divided by 0.75. Okay, so we get this decimal number, and notice that's bigger than 1. So you should know that the range of sine is between -1 and 1, and that has no solution. So the mathematics supports the fact that what we were seeing is this looked like it's probably going to be too short. And don't just go by this is shorter than this, right? We really would have to find the height to be able to tell if this is too short or not, or use this law of sines. So we don't really need the height if we do this. This supports that, and so this has no solution. And of course, if you try to use sine inverse here, it'll give you an error because that's not in the domain of sine inverse. So this is our case where there's no triangle formed. In B, we've got beta given, right? 26 degrees is a little smaller. Your triangle doesn't have to be perfect, but try to be somewhat reasonable. Okay, So B is what's across from it, and then A is 18, so that's what I'm going to put up here, and I don't know the base. B is 11, that's shorter than 18, but you know, so the question is, does it reach here? Is it exactly the same length as the height? And if it reaches here, it will also reach here. So is there 0, 1, or 2 triangles? If this, so this is B equals 11. If B is longer than 18, then it's got to be way over here. There'd only be one. Then we would know. Without even using the law of sines, we would know if this is like 20, for example. But it's smaller, so we don't know. We need to use math. So we'll use the law of sines. Sine of 26 degrees over 11 equals the sine of, so this is A, so I'm going to use alpha over 18. So sine alpha equals, so it'll be 18 sine of 26 degrees over, so cross multiply, the 11 would go here, but then when you divide by 11. So 18 sine of 26 divided by 11. So sine alpha equals 0.71733. Don't round that. I'm just writing it down for reference, but use the value on your calculator. So this is smaller than 1. That means this has 2 solutions. If this equals 1, then there's one solution, because then we'd have a right angle. Sine of 90 degrees equals 1. But since that's smaller than 1, 2 solutions. So that's how you're going to tell. Bigger than 1, no solution. Equals 1, 1 solution. Smaller than 1, 2 solutions. And these should always be positive, right? Sine is always positive in the first and second quadrant if you put the angle in standard position. So sine of an angle from 0 to 180, doesn't matter if it's acute or obtuse, sine is always positive. Okay, so how are we going to find the 2 angles? There's 2 solutions. One is this one, and one is this one. I call that A, so I'll call this one alpha 1. Alpha 1's acute. Alpha 2 is obtuse. Well, alpha 1 will equal the sine inverse of this number. And again, I'm not going to actually round. I'm just going to use the number on my calculator. So that's going to be my acute one. So sine inverse answer, 45.8 degrees approximately. The other angle, the other solution, is going to be, so notice this is actually alpha 1. It'll be 180 degrees minus alpha 1. I should use approximately here. I should have wrote smaller, and why I wrote so big. Now I'm going to run out of room. Okay, so 180 minus the answer I got here is 134.2 degrees. So there are 2 solutions. Now we have 2 cases, we have to solve them separately, okay? So let me put like a little note here just to make sure we're clear. These are coterminal angles. All right, so we now have to find, let's see, we've got beta was given, so we need gamma. So there's going to be 2 gammas, this one and then this one. So one's bigger and one's smaller, right? So gamma, if this is alpha 1, gamma 1 will be the larger angle, gamma 2 will be the smaller angle. And then we're going to have 2 sides for, or 2 lengths, I should say, for C, C1, C2. I'm actually going to pause the video now, so I need to get some paper for, well, I guess I could write on the back of this. I need to go do something quick anyway, so let's pause the video, and then when I come back I'll show you how to finish the problem.